Alright guys, thanks for coming back to Eli UW. Today we're going to be covering first order ordinary differential equations. Okay, so before I had already covered a lesson on second order differential equations. I went over the method of undetermined coefficients, really good method, and the characteristic equation for a second order differential equation. So now we're going to do first order, and they're much easier. These are the methods we use. So the first is separable, ODEs. So a separable ODE has a specific form. It has a form y prime equals g of x over f of y, where this y prime is dy dx, or it could be dy dt. It's dy. It's the derivative of y with respect to any of your independent variables. So we can now multiply by f of y and insert this definition of y prime. So this looks like dy dx times f of y equals g of x. And now, like I in a video I did before, we can treat these derivatives like fractions, and it really doesn't change anything. So we can write this as f of y dy equals g of x dx. And now you see why it's called separable, because we separated the ODE into two parts, something with just x's and something with just y's. And so now to solve this, we just integrate both sides, right? And so now this function of y, we'll get this antiderivative of y, and we'll have to manipulate it so that we just get y of t, right? So now let's say f of y equals 1. That's possible. We'll go up here. So if f of y equals 1, we just have dy equals g of x dx. We're going to integrate both sides. And so we're going to get y of x is the integral of g of x dx. And so now usually when we do indefinite integrals, we would get a plus c, right, for each integral. But because there's two, we're just going to combine it into one big constant, c, right? So sometimes we write the antiderivative as a capital. So the answer is y of x equals g of x, the antiderivative of g, plus c. That's it, if f of y equals 1. Okay? And we'll see an example where f of y is not 1 later on. So that's it for separable. The second type is a linear first order ODE. Linear. We'll see why it's called linear. So this has this specific form, y prime plus a of ty equals f of t, where f of t, as I explained in the second order differential equation video, is the forcing function. So the reason we call these equations linear is because this coefficient a of t is a function of t and not of y. If this was a function of t and y, or a function of y, then we might get a y squared term, and then the equation wouldn't be linear. We can't solve it using this method. So we're going to do a proof, and the proof will lead us to a formula that we can use to solve equations of this type. And also, just to remind you, if there was a coefficient in front of y prime, we could just divide it out. If it was a function, like if it was t, we could divide it on in the whole equation, so we would just get the coefficient of 1 in front of y prime. So the proof of this is pretty easy if you know the trick. And the trick is you just have to multiply each term by something we call the integrating factor. We define that integrating factor as e to the integral of a of t dt, right? So let's do that. So we'll do e to the integral of a of t dt times y prime plus e to the integral of a of t dt times a of ty equals e to the integral of a of t dt times f of t. Okay? So if you stare at this left-hand side long enough, you actually notice it's a total derivative. So we can write it like this. We can write it as d by dt of e to the integral of a of t dt y, which equals, we'll just leave the right-hand side alone, e to the integral of a of t dt f of t. So how can we check this? We just use the product rule, right? So the product rule says that if there are two functions, the first function is e to the integral of a of t dt, second function is y, we take a derivative of the first, leave the second alone, then we take a derivative of the second, leave the first alone. So now do that here. If we take a derivative of e to the integral of a of t dt, we're going to get an a of t back. We're going to leave y alone, and then the integral of e to the x is, the derivative of e to the x is just e to the x. So that's that second term, right? And then if we take a derivative of y, we're going to get y prime, and we're going to leave this guy alone, and we're going to get this first term, right? So now all we have to do is integrate both sides. Now from the fundamental theorem of calculus, we know that this integral and this d by dt, they just cancel, right? And so we have, now I'm going to insert our definition of the integrating factor because I'm tired of writing e to the integral of a of t dt. So we have I of t times y equals the integral of I of t f of t dt. And this should be a dt here. Right? So now we just solve for y. So to do that, we divide by I of t. We find the inverse. So y of t equals I of t to the minus 1, the inverse of I of t, times the integral of I of t f of t dt. And that's it. That's our formula. Proof. Okay, so now let's do some simple examples. So example 1 will be y prime equals x over y. Okay, so this is dy dx equals x over y. And again, we want to put this in the form, in the separable form. So we would just have y times dy equals x times dx. We integrate both sides, right? Let's do that over here. Integrate both sides, you'd get y squared over 2 equals x squared over 2 plus c, right? So these 2's cancel, and we're multiplying by 2, but this c is a constant. It's not going to change by multiplying by 2. It just becomes a different constant. We'll just leave that alone. So we have y squared equals x squared plus c. But now you say, this is y squared. How do we get the solution y of t? Well, we just take a square root of both sides, right? So we actually have two solutions. So y of t will equal plus or minus square root of x squared plus c. That's our final answer. Okay. So now let's do a linear one. So let's say we have y prime minus 1 over t y equals t squared, right? So now these linear ODEs actually become very simple. All we have to do is find I of t and plug into the formula, right? So what's I of t? I of t is e to the integral of minus 1 over t dt. Now, I picked 1 over t because when we integrate 1 over t, we're going to get a ln. And e to the ln will just be, e to the ln t will just be t, right? But it's not going to, but we have this minus here. We notice that we define this integral as e to the a of t dt. But this a of t has a plus in it. But in our example, it has a minus. That's why we have this minus here. And that's going to change things. So this becomes e to the minus ln of t, right? And now from properties of logs, this minus goes inside, right? So this becomes e to the ln of 1 over t. And so, again, e to the ln of whatever is just whatever's on the inside of the ln. So the I of t, our integrating factor, is just 1 over t. Okay, so now we're just going to plug into the formula. So y of t, let's rewrite the formula, is I of t to the minus 1 times the integral of I of t f of t dt. So now let's find what I of t to the minus 1 is. So I of t to the minus 1, it's just, we do 1 over t, so it's t. Simple. So Plugging into our formula, we have t times the integral of I of t, 1 over t, times f of t, that's our t squared, dt. So we have 1t cancels, right? So y of t is t times the integral of t dt. The integral of t dt is just t squared over 2 plus a constant. So y of t is t times t squared over 2 plus a constant. And our final answer is y of t equals t cubed over 2 plus ct. And that's it. So thanks for listening, everyone. And if you have any questions, please feel free to put them in the comments.